Not like these guys have.
All right, so I'm recording now, and if you record, then we'll be all set.
Yeah.
So I realized that we haven't had 5 labs yet, but what I decided to do is make everything consistent. So it'll be numbered after the week. This is the 5th meeting. So from now on, it'll just be numbered after the week. So this is going to be lab 5. So I guess that means we didn't have a lab 2. So lab 1, lab 3, lab 4,
Yeah.
lab 5.
So lab 1 to 2
Did anybody else download the data for today yet? Did it work for you? It looks like it's.
I tried to pull it up in an art map, I just had it downloaded.
You just have it downloaded?
Yeah, I'm gonna try to pull it up.
Said that it has the right number.
Didn't have it right.
Yeah, it has the right number.
Huh.
But didn't offer you to create the thing?
Yeah, it's a off.
It sounds like the pyramids are corrupted, which happens sometimes. So, oops. Oh, there it goes. So did it eventually show up or no? Okay. If you ever get like a layer that shows up, but it doesn't look right, or you get a message about the pyramids that's not just, can I create the pyramids? You can delete this. Well, if it's an image file. Wait, I'm gonna change this. If it's an image file, you can delete this OVR file. That's the pyramids layer, and then that forces it to recalculate the pyramids, which are basically just like a bunch of different views of the data. It's like it's pre-loading and pre-calculating different views of the data so that when you zoom in and zoom out, it's faster. You're not deleting anything that it can't recreate. Again, if you do delete that, it will ask you if you want to recreate the pyramids or create the pyramids. All right, so this is the data we're going to use for the lab, and I'm going to talk about it during the lecture, because what we're going to do, which is what we've been doing a lot, is kind of walk through examples as we go through the class, and then the lab kind of builds on all the examples. So here is the data, and then the other layer that I'm loading is the imagery, the world imagery. So nice that we can do this. I remember, when I started doing this, you couldn't just load the free imagery that existed for the entire world in the background, kind of give you a reference of where you were. So this is Laguna Beach, California. I just chose this area because it's more varied than our area. So we could have done our area, but since we're talking about terrain and slope and aspect and things like that today, I thought it'd be a little bit more exciting if there was some terrain. It's kind of interesting, this little piece of land right here, which is probably only a few square miles, has more elevation variation than our whole state. We've got the ocean down here. So this area right here is at 0 elevation, and then this ridge line is close to 1,000 feet up here, and people live all along it. This it is labeled on this. It's hard to see up here, but this label says "Top of the World." And so my nieces and nephews, they go to elementary school up here, and this elementary school called Top of the World, which is kind of a funny name. But if you're up there, because the rest of Orange County, where I grew up over here, off to the east of this. But the rest of Orange County is a little bit lower. Okay, these are some very coastal mountains with a canyon to get you down to close to the ocean. It's one of the last like open areas in Orange County that's not up against the up against the other mountains. But yeah, so from here you can see almost all of the rest of southern Orange County if you look out to the east. And so that's probably why they called it that. But anyway, these are all homes. It's kind of like what you might picture Italy or Spain. This is Mediterranean area with these mountains. This mountain that just comes down. You can see that in the elevation data. Got a few canyons. This is the main canyon, and we'll actually see it in greater detail as we analyze it using the methods that we're going to talk about today. X. Close that one. I guess that's not closing. Oh, that's. I thought I'd already downloaded the lecture. I guess I have. I just hadn't opened it. So today we are going to be discussing terrain modeling, and although I chose a different area for the examples, this is really applicable anywhere. I mean, when you have everywhere has elevation, it's just not as dramatic, let's say. And so, in fact, the image that I use on the left is the image I use on every single first slide in this course, and that's a digital elevation model of the state of Mississippi. This table is from the book that we teach 217 with, and just bring it up here as a little bit of a review. You probably, if you've taken an introductory GIS course, you've probably calculated some of these already and discussed what they are, including slope and aspect. Probably the two most important ones. We're going to discuss slope and aspect. We'll discuss visibility a bit. We'll discuss some of these others later in the course, particularly flow length and upstream length. We're going to go into a little bit further detail. So even if you hadn't ever calculated slope or aspect in any previous course, or visibility, or hill shading, don't worry, because we're really going to kind of dive into the math and understand how they're created. So these data sets that I've shown you so far, both the one of Mississippi and the one of Laguna Beach, California, they're often referred to as digital elevation models. It's kind of a general term where every cell in the raster represents a height, and that height can be relative to a vertical datum. So sometimes you'll hear the height referenced as sea level. Sometimes you'll hear it referenced as the height above an ellipsoid or the height above the geoid. So those are really the three different things that it could be. It doesn't matter a whole lot for comparing it to, but when you compare it to other data sets and when you compare it to actual sea level, that's where it matters. But as long as the internal accuracy, in other words, a meter from this cell to this cell is really a meter, then you're fine. It doesn't really matter if it says 27 in one and 26 in the other, unless you're going to actually do some comparisons. Where do we get these sort of data? Well, that actually matters a lot because it plays into how this data gets used, and also what the data itself means, the accuracy of the data. So photogrammetry is a very common, was particularly actually, 20, 30 years ago, that was probably the most common method for collecting digital elevation models. And that involved taking an airplane, flying it over a particular land area, and then using the difference in the different images to model the three-dimensional changes in the ground, much the way our eyes actually see it. But the computer can quantify that sort of information. And there's actually a way to do it even without computers, which we don't really teach anymore, but it has been taught in photogrammetry courses in the past. Okay, but today, photogrammetry for creating digital elevation models is actually coming back because of the rise of drone photography. So here is an example of that. Here's an area in the Dominican Republic. Here's an elevation model that's been created. The bluish and greens are lower, and the higher elevations are the reds. And in this case, it's by the ocean, and it was in a mangrove swamp. So almost all of the high elevations are really treetops. The low elevations are where it's clear to the ground. But these images were created from, oops, that's not what I meant to do. These images were created from all of these individual images that will come up here in a second. So these are all individual images that the drone took as it flew back and forth over this area, collected a bunch of individual images. They're higher resolution than this, but they take a few seconds to come in as full resolution images. But as long as there is some overlap, the more overlap, the better. We can create a elevation surface. That's not what I meant to do. We can create an elevation surface with the differences, knowing the differences. That software called Pix4D does those calculations. There's other software that does that. It's referred to as soft copy photogrammetry. Yeah.
It says your presentation is paused. I'm sorry to interrupt.
Okay. So can you unpause it, or do I unpause it?
Okay. Yeah, I wasn't looking at the computer, so I'm still recording. The only thing I can pause here is the recording.
Mine says pause recording, so Zoom recording.
My recording is running.
Is it running? Is this number increasing for you?
Yeah.
Okay.
It's just the presentation. I think the sharing or screen thing is paused.
Currently sharing. Recording in progress. I don't know what so you're not seeing anything move?
I just have a blank screen saying the presentation is paused. In the middle of it.
I don't know. Do you want to start it over? I mean, mine says it's recording on this end.
Now, okay.
Now it's working?
Uh-huh.
Okay. I just restarted the sharing, stopped it and started it again. All right?
Mm-hmm.
It's going now?
Yeah.
Okay. All right. There are other methods for creating digital elevation surfaces. One is LiDAR. It stands for light detection and ranging. And that acronym was actually built on radar, it's the acronym, which stands for radio detection and ranging. And they have some similarities, but they're fairly different in how they operate. LiDAR, light detection and ranging, works by sending down lots of pulses of laser light toward the ground. and then measuring the travel time back. And so it basically bathes the Earth in points. And many of the data sets that you get nowadays, the high resolution data sets that you get nowadays, are created with LiDAR, including the one that we're going to use today, the Laguna Beach data set. Radar works a little bit better when the need for resolution isn't as great, lower resolution data sets. Radar does have the advantage that unlike LiDAR and photogrammetry, you can tune a radar instrument to actually penetrate different objects, including tree canopy. And so, for example, one of the most massive undertakings of a radar mission was the shuttle radar topography mission back in the early 2000s, I believe. It could have been the late 90s, but I'm pretty sure it was the early 2000s. They launched a space shuttle, and they put a radar instrument that actually collected elevation for most of the Earth, except for the polar regions, using interferometric radar, meaning that it was looking at the difference between two radar returns, kind of like how we use photogrammetry. Finally, for a smaller area, we can just do a simple survey. We could survey points out in the field using a GPS or a total station device to get elevations and actually get points at key locations. So, you know, if you're looking at the elevations over a particular area and you measure the stream bank, make sure that that's in there. You take a few other key locations for their elevation, you can turn that into a digital elevation surface. So the error on all of these is different, and it does depend on lots of different factors. One of them is the resolution. Generally, you get better resolution from a LiDAR data set. However, from a drone data set, you can get a pretty high resolution in photogrammetry, but you're not going to be able to penetrate the canopy very well using photogrammetry. So kind of like going down this way, photogrammetry doesn't penetrate the canopy hardly at all. LiDAR does a bit, and radar can, depending on the specific wavelengths that are used. Radar can penetrate the canopy quite well. And then survey actually has no problem with the canopy, but you're not collecting a lot of points. We are going to talk about this word here, interpolation, later in the course. But interpolation is basically the process by which we take all of these produce points in space. We take those points in space and turn them into a surface. Really quickly, here's a couple of definitions. Digital elevation model is just a set of regularly or irregularly spaced height values on the surface of that represent points on the surface of the Earth. Sometimes you'll hear the term digital terrain model, and this term didn't come into play until we had really high resolution data sets that were capable of detecting the Earth, very small portions of the Earth, at very high accuracies. And basically, the digital terrain model is the map of the terrain itself, where we've removed different objects from the ground. And so here's some examples of LiDAR data, a few more examples of LiDAR data. This is a little bit colorized. But you can see here, these are, what do you think these areas are in the LiDAR data here? What's different about those and these? What's that? Yeah, so these are treetops. So these are forests, and are right next to a stream. There's not a whole, you'll notice that in LiDAR data, and actually in photogrammetry, you don't get a lot of points in the streams themselves. Okay, so these are fields, much more smooth. Okay. the accuracies and the resolution can get down close to 2 centimeters. Of course, that it really it's really important that you ask what is that measuring? Is the actual point there measured within 2 centimeters, or are you saying that the ground surface there is within 2 centimeters of that? Because obviously there's not a whole lot of those measurements here, the ground surface, and so we're not within 2 centimeters. So there are scientists that actually study, okay, well, in forested areas, how accurate are we getting to the actual ground surface? And it's much higher, okay? Sometimes on the order of a meter or so from the actual ground surface. So, like I said, we're going to spend a week talking about actually taking surfaces or creating surfaces from a series of points later. But in general, there are two main approaches. One is that we take the points and we use some algorithm to create a regularly sampled grid, sometimes referred to as a lattice. This is a raster. This is what we're going to talk about today. But I just want to let you know that there is a very commonly used alternative that's not a raster data format that basically creates what they call a triangulated or a triangular irregular network. Okay? And in a triangular irregular network, the original samples, the points, are preserved. Those are used. Basically, it makes a network of these triangles called Delaney triangles. And those triangles, the algorithm that creates those triangles attempts to create triangles that are the closest to an equilateral triangle as possible. So, it can't always. I mean, some of these are very far from an equilateral triangle. But the reason why it chose this triangle instead of choosing the triangle that went like this was because these two triangles were then slightly more like a equilateral triangle than if it had drawn the line between there and there. So the tin, that's a tin. This is a DEM. It's usually created through interpolation. In other words, the raster is created and then it's filled by some algorithm. Every point by point, cell by cell, an algorithm is used to determine what the value of that cell is going to be. You could use the nearest point. You could use the average of the 2 nearest points, the average of the 3 nearest points, the average of the 4 nearest points, the weighted average of the x number of nearest points, and so on. Those are all interpolation algorithms that are used and that we'll discuss further when we talk about interpolation. But it just goes cell by cell. Yeah.
Just to clarify, so it's taking the points, creating a raster, and it's assigning the values in each cell from those points?
That's correct. That's the spatial interpolation in a nutshell. Exactly. All right. So the digital elevation model, the raster that we're going to use today, these are some of the advantages and disadvantages of using digital elevation models. So one of them is that it accepts data direct from digital altitude matrices. In other words, if we have regularly spaced data, then it fits well into a digital elevation model. If we do have irregular data, then it has to be resampled. In other words, this is irregular data. To create a surface from it, it has to be resampled. And so, what's that? Irregular? Not evenly spaced. So one of the issues is that depending on the algorithm used and the resolution, it can miss complex topographic features. In other words, if your data has a spike or a valley, a regularly spaced grid may completely ignore one of those features. And then in areas where it's very flat, you've got lots of cells holding a very similar value. So you have lots of redundant data, you could say. One alternative to that, and there are lots of, like a TIFF and other formats, will be able to compress the data in those areas. So it can store those data very efficiently and make them smaller. The main advantage is that it's less complex, so it's a pretty easy process to explain. A raster is, and going row by row, column by column is not very CPU intensive. Once those pyramids are built that we talked about at the beginning of class, they display really rapidly. TINs, on the other hand, if you were to load a TIN with a bunch of LiDAR data, it takes almost the same amount of time to load that than it would be to load the individual points. Have you ever loaded a data set in a GIS that has like several million points in it? Yeah, it takes a little while to load, and the TIN does the same thing. In fact, sometimes it takes a little bit longer. But the main advantages here all basically can be summed up by saying that the original points themselves are not are preserved in that format. They're preserved, and so it won't smooth over hard or complex features and things like that. However, there have been scientists who studied the issues here, and for the most part, for most applications, lots of studies show that the effect of having these triangles rather than a smooth surface is sometimes a problem. Can be as big of an error as creating the smooth surfaces. It's almost like a trade-off. But there are situations where, let's say we had a hard cliff, and you were able to go around with your survey line and get the edge of that hard cliff. Well, obviously the TIN's going to do better in those cases. So if you do have hard break lines, TINs work well. So,
Real
yeah.
Quick, can you explain through sampling? It's in the two examples of advantages and disadvantages. Does that mean going out or getting new imagery, or going out in the field and getting new points?
Okay, so resampling in a remote sensing or GIS terminology means to basically the points that were collected through LiDAR or photogrammetry are the samples. So those elevation data, each of those points is a sample. And right now, they're randomly, well, not randomly, but they're distributed kind of chaotically on the page. And so if I was to turn those into a regular set of values in rows and columns, the general term for doing that is resampling.
Okay.
I'm taking the samples and I'm placing them in a different location, but I'm using the other version. Now, whether you realize it or not, the process of changing a raster's projection from one projection to another is a resampling process, because the raster, those cell values represent the value at the center of every cell. And so if we change the projection, what we're doing is creating a new raster in a new location. Okay, and then we're going cell by cell and figuring out which old cell from the old raster and the other projection best fit inside the new rows and columns. And so even in that case, we're going from a regular grid cell to regular grid cells. It's not that we're going from pseudo-random to regular, but they're both resampling. So if somebody says one of the weaknesses or one of the drawbacks of doing X, changing the projection, whatever, is that you have to resample the data, what they're saying is that you're doing, whenever you resample, you're doing something that makes it impossible to recover the data unless you still have keep a copy of the original data. You're changing the values. Okay, even if you're not changing the cell size, there's not a one-to-one comparison in terms of, because when you change the projection, it's going to be warped in space, it's going to be expanded and contracted in areas, and there are going to be places where it has to skip a value. And so it's like, it's best, let's say we had a LiDAR data set. Okay, we collected the LiDAR data set in a certain projection. We converted it to a raster grid cell in projection X. And we needed that in projection Y. It's actually better to go back to the raster data set and resample the raster data set into projection Y rather than taking the raster data set you created in projection X and change it to projection Y. The reason is because you're making two copies. You're resampling it twice in that way, whereas you're only making one copy of the original data in the second version. Sometimes it's unavoidable. We don't have a copy of the original data. But resampling is destroying some original data. So that's what resampling means. And so with a tin, you're keeping the original data, the original points, without modifying those original points. All right, so it's interesting that now that I did that, this is like different. Like what I see is different on my screen. Anyway, height or elevation is used in a lot of things. This is one of the primary layers that you see. You know, lots of government organizations. Everybody uses height. It seems like, or elevation. So we're going to talk in this class. We'll talk about water modeling the surface of water over the earth. We've already seen that height or elevation could be an input to cost surfaces, which are part of site planning. It can be used in conservation. That's one of my areas of research, so I threw it up there. We use height a lot, and then infrastructure development, building roads and things like that requires this layer, this height layer. So, like I said before, there are many different terrain derivatives, but the most important are slope and aspect. So how do we calculate slope? Well, this is kind of like high school geometry explanation of how we calculate slope, right? What is the slope? Like what's just a general definition of slope? What's that? Coast?
Change in elevation.
Yeah, change in elevation. Mathematically, how would I describe a change in elevation?
Rise divided by run.
Rise divided by run. So run is like XY space, and rise is elevation change. So mathematically, we can calculate slope in degrees here as just the rise, the A here, divided by the run, B. So does slope really exist? Like, if all we know is a single value of elevation, can we calculate slope? Just one value. If I know the elevation is 50 right here, what's the slope? Yeah, I don't know the slope because I don't know the values around me. So in order to calculate, slope is really a neighborhood operation, or it's going to be, because we need to know what the slope is. So we could calculate the slope between any two cells, right? So I could calculate the slope between, if this was 50 and it was 49 right here in two different cells, then I can just plug that in the formula. What's the rise in that case? 50 and 49. 50 here and 49 here. So what's the rise between here and there? 1, yes. All right, let's say the cell size was 1. Okay, let's just say it was. So this would be 1 divided by 1. We take the arctangent, we get slope in degrees. We don't even have to like really figure out what that is. But what is it? If this is 1 and this is 1, what's the angle here? Everybody know? What's that? If this is 1 and this is 1, what's this angle? In degrees. Like, so the answer to this formula. 45, that's right. If you don't even have to really calculate that out, right? What's this angle right here?
90.
Right. And so if this is 90 and these two are equal, which they would be, because if this was 1 and that was 1, they would be equal, they would be 45. All right, but you could calculate it out and it would work. All right, so in GIS, we could do the slope from every different, like the slope from here to here would be, the rise would be 4, because 48 minus 44 is 4, and the run would be whatever the cell size is, but we would have to store that value like right here, and the difference between this one and this one, we'd store that value right here. The difference between this and this one, we'd store that value right there. So that presents a problem because typically we want our output to always be in the same rows and columns as the input. So we could say, what's the slope right here? Because we know the elevation is right there. You also want the slope in that location. We don't want a different pattern for our slope values. Okay? So, what we do, and in addition to that, what we're trying to measure is the steepest slope. In addition to that, the slope may not fall exactly parallel to the rows or columns. So what we want to do is calculate the slope at this location. All right, there's several different methods that have been proposed over time. We're going to talk about the two most common methods. One is Fleming and Hoffer's, sometimes called the 4 nearest cells. And the other is the third order finite difference, which is Horn's method. Okay? All right. Now to get there, I know we've already shown this slide, so we'll go through them quickly, but we're going to talk about kernels again really quick. Okay? A kernel, remember, is the moving window. This is going to end up being a neighborhood operation. All right? It's going to be, what happens with the kernel is multiplied by all of the cells that it corresponds with. And then you put in a function to combine all those values. So if we say sum, it will multiply all these and add them all together. If we say mean, it'll multiply them all and take the average, right? I forgot what all the other focal statistic functions were, but some of them aren't even valid. Like the ones we talked about last week, majority and variety, those aren't valid. Because this is math, it needs a mathematical function to combine them. All right. So in this particular function, which we talked about before, here's the kernel for high-pass filter. It multiplies everything in the window by -1 except for the center value, which it multiplies by 9. And then to combine them, it multiplies everything by 1/9. So it's taking the average value. With the slope kernel, one more time. So this is the edge detection kernel from last week that we talked about. The edge detection just can look at the difference between the value to the west and the value to the east, or the value to the north and the value to the south. Or we could modify it, and it could calculate the value going from northeast to southwest. Those are all different ways that we could do that. We're getting actually pretty close to slope, right? Because slope is looking at the change in elevation through that cell. So a kernel like this is looking at the change in elevation from north to south, if we're talking about a DEM. This is looking at the change in elevation from east to west. So we've looked at basically the rise from north to south and east to west. Those values calculate the rise part of the equation, east, west, north, south. Or sorry, other way around. So this is the slope kernel, and it's exactly like the two kernels before. It's actually two kernels. You calculate the slope change from east to west, and then you calculate the slope change from north to south. And you get, right here, the rise portion of the equation. So you can see 40 minus 49 is the rise portion of the equation from here to here. And then 45 minus 48 is the rise portion of the equation going north-south. And then finally, to get the run, you divide it by 20. Why divide it by 20? The cell size is 10. So you divide it by 20 because it's going across two cells. Two cells, two cells. So you divide each by 20. All right? And then this equation right here is very similar to the rise over the run from before, what you do with it. But what we're doing here is we're adding the squares of both of these values. So we're taking basically the difference in z over the x and the difference in z over the y, which is there's two different rises. And then there's only the run's the same on both cases. And we're squaring both of those, adding them together and taking the square root. It's very similar to finding the average, but it ensures that everything's positive. That's one reason that it's doing it. And also, basically, it'll make big differences even bigger. All right. And then finally, we take the inverse tangent of that value and we get a number, 25.53. All right, that's the basic formula for slope. That's what it does to calculate slope. Now the other method is a different kernel, and this kernel actually weights the center cell higher, but takes into account all of the east-west changes and all of the north-south changes. So we're going to implement one of these right now. I think I said we're going to do this one in the lab. So let's do that one. This one's actually a little more complicated. All right, so we're going to calculate slope by hand, and then one of the things we're going to do is verify that it actually worked using the slope tool from our toolbox. All right. I added it by going right here and saying add base map.
And that's the word imagery, right?
That's the world imagery with labels. I don't know that the labels matter that much.
And what about that reference?
Oh, it adds that when you say world imagery with labels, it adds that. That's why the labels show up on top of the.
Is it David transparent?
Yeah, it only has labels on it. Yep. All right. Okay, so because we're going to end up doing this in the lab, let's go ahead and create a toolbox called Lab 5. Create a new toolbox called Lab 5. So I got my Lab 5 toolbox. You're going to end up creating three models for this lab inside of Lab 5. And really, you can just modify the one that we're going to create right now to do task 1 in the lab. So you only produce 3, or you could produce 4. You could copy and paste and start it brand new. So I'm going to create a new model in here, and I'm immediately going to close it, and then I'm going to rename it. I'm going to call it M slope for manual slope. I'm going to calculate slope manually. I didn't just call it slope because there's already a tool called slope. All right, now I'm going to open up this thing and edit it. So we need to implement this kernel right here. And then we need to do this other math. So once we implement this kernel, what happens is that we'll do all this math, because the kernel will multiply everything by everything in the kernel. -1, 1, -2, 2, -1, 1. It'll do all that multiplication and adding them together. So it'll do this adding them together. Okay, but it won't do the dividing by 80. Won't do that. And it won't do this math right here, the squaring and the square root. Okay. All right, so our tool is going to start off by doing the the focal statistics, spatial analyst tools, and focal statistics. Focal neighborhood, focal statistics. I'm going to put that on there. We're actually going to need 2 of them. All right, so let's go inside there. And the elevation data set is going to be the input raster. And then we need to select weight, because the weight is what's the kernel. Here's the kernel file that we're going to choose. So what we need to do is create our kernel file. So let's open up Notepad. Notepad comes on every Windows machine, so you should already have it. If you read the help here, we'll see how the kernel file needs to be. Now, I messed up. Remember that was it the first or the second week when we talked about operations? I chose irregular instead of weight. It's weight that you need to choose, not irregular. All right, so your kernel file needs to look like, this is kind of small. There we go, I can make it bigger. Needs to look like this. This is the number of rows and the number of columns in your kernel. If we go back here, yeah, it's going to be 3 by 3. This is the kernel for slope. Both of them are going to be 3 by 3. So it needs to look like this. And our kernel, though, is going to look like this. -1, 0, 1, -2, 0, 2, -1, 0, 1. So in Notepad, we're going to change this. It's going to say 3 space 3, and then I forgot it even though I just said it. Okay. -1, 0, 1, -2, 0, 2, and 1, or -1, 0, 1.
Spaces in between the numbers?
Yeah, just spaces, nothing else. No commas, just spaces, like this. And the help does say that somewhere. ASCII text file that defines number of cells. A space between each value is necessary. All right. Then let's save this. I'm going to save it in the same folder I've been working in, which is called C temp essay week 5, and I'm going to call this I'm going to call this was this the change in X or the change in Y?
This is changing it.
That's correct. Yes, the change in X. So I'm going to call this, it's really the change in Z over the change in Y, right? Well, it's the change in Z in the X direction. That's what it is. So I just called it DZ.
Would it be correct to say change Z over X? Would that be a correct way to say that?
Yeah, that's fine. It doesn't really matter what you call these as long as you can keep them straight. Maybe I'll just call it, well, I'll just leave it the same, the way I had it. Just so that I know that this is the X change. All right, then save it. And then modify the kernel so that it goes the other direction. So here we have -1, or actually, let's look and make sure I'm doing this right. Nope, it's the positives on top. 1, 0, 1, or 1, 2, and then 0, 0, 0, and then the negatives on the bottom. Now, make sure you do not just press save. You have to say save as. If you press save, you'll save over your other one. Save as and call it Y. Okay. So one's called, I called one DZ DY, and the other one DX DY. At that point, you can close these. What does this say right here, by the way?
It said that the mask layer, invalid weight neighborhood mask.
Okay. So we're going to choose our, let's choose DZ, what, sorry, did you have a question?
Can you bring back up the Excel?
The which one?
The second one, change in.
The Notepad? Which one, the Y?
Yeah. And we change this one, we save this one as.
I called it DZDY. All right. All right, let's think about, so this is where the output's going to be saved. I guess that's okay, although we could save it in the folder we've been working in. The weight is the correct choice. This is the difference in X. What is the statistics type here that we should do? we want to, let's think about what we want.
But Red, were you doing the X change first?
Yeah. I guess it doesn't really matter which one. But, you know, now that you say that, we do want to know these things. So I'm going to go, I'm going to call this dx. So to change in the x. So I did save it so that I'll be able to look at it and know what it is. Okay, so what's the statistic type that we need? Let's look at the formula here. So what we want to do is we want to take the kernel, multiply it by everything, so that it creates this portion. So it'll be 1 times the difference between this, 2 times the difference between that, 1 times, that's all going to work. Okay? But we want to add them all together. That's what we want to do. So what's the right choice for adding them? The sum. Yep. Now, I'm gonna say we could choose the average, but only if the number of cell size, only if the number of cells for some reason was exactly what this value should be, which I mean, it's not going to be that, because we are going to divide it by something, but it's not going to be that number. So we need to do that ourselves, not rely on that being the same. Okay. All right. So once this is done, it should be fine. There aren't any no data values in the cells. There actually were some no data values when I filled them. They were small. So there aren't any no data values in the cells, so it doesn't really matter if we click that or not click it. So once that's done, we could say OK, and it'll have that one done. I'm going to go ahead and run this right now so I can see the result. I didn't add it to the screen. I'm going to add it automatically. I'm going to add it manually. All right, so this represents, I'm going to turn the base map off for now because it takes forever to load. But this represents the difference in x. Sorry, I didn't mean to cut you off. Go.
You didn't get an error running that?
No. Did you get an error?
Yeah, I must have.
What is your, no, just tell me what your error was.
Invalid weight, neighborhood max, syntax error, syntax error.
Okay. Can you send me?
Typed in my notepad wrong.
Yeah, can you send me your notepad? Send it by email or look at it and see if you can see the error. But yeah, that's the error for sure. Well, it's what it says it is anyway.
Okay. I was missing a comma on my pasta reads.
You shouldn't have any commas.
Okay.
Everybody else's work or no?
Mine worked.
Cool. Yeah, you're not zoomed in. Oh, that's your zoomed in everywhere, right? I mean, you're not zoomed in at all.
I mean, it added this really smooth layer over, like, this one. That one, the text box. This one.
Yep, that looks right. Yeah, I mean, I must, because I'm zoomed in.
Yeah, yours is a little darker.
So mine's in a little different spot. But in general, what you should have Oh, wait. Don't put that in here. No, just put that there. Go down. Use some. Okay, good. Just make sure everything's the same. All right. So in general, why do things like this show up brighter than see how dark it is in some areas?
Showing the rise.
It's showing the rise. So that's exactly right. White means what? A big change in which direction?
Elevation up.
But in this direction, north, south, or east, west?
Because D's and yes, it changed it.
Yes, east, west.
Oh, so it's kind of angles.
So basically, it's going to be brighter in areas with a big east-west change and darker in areas with a small east-west change. So I have like the edge of this cliff, the edge of this cliff over here because it's going this way, this cliff's going that way, all right? So now if I run the other one, I'm going to set this one up exactly the same. I'm going to say the elevation is the input. I'm going to say the rectangle, the weight. I'm going to choose dz dy. Make sure that I say sum. I'm going to save this as dy. It should be all set.
Dr. Grazer, I've got everything exactly like you do. I keep using this weighted mask error.
Okay. Could you send me your mask?
The current file.
That's correct. Okay, look at that one. That one looks different. What are your ranges? Are your ranges the same? Because yours does look a little different, but if these are the same, then also the highest and the lowest number. All right, Adam. Yeah.
It looks like on your model builder that you have the Laguna Beach elevation tip. You only have one of those that is connected to both your focal statistic.
Yes.
Do you have to do that, or if you have if you just copied the first one and made a second one, will it work the same?
It will work the same, but the advantage to doing it this way is that if I right-click on this guy right here and make it a model parameter, then somebody can put in the elevation data set. I only have to do it once. So either way will work, but this is a little bit, probably, I would say probably better. I don't know if better is the right word, but this is a little more elegant than having two different, because they are the same data set. So having them on there twice means that if you made both of them a model parameter, they'd have to specify the data set twice rather than just once.
So another quick question, Dr. Raver.
Yeah.
What I did is I just deleted the second Laguna Beach one in the model builder, and then ran the connect tool from the first one to my second focus statistics model. Do I select it as an input raster? Would that be the correct thing to select?
Yes. Yep,
Okay.
the input
I want to
raster.
make sure.
And then it'll link them up.
Okay, and we do make the elevation our model parameter.
I got the same problem.
Yeah, well, I was planning to do that later, but yes, you can do it right now. So I was planning to make that kind of the finishing part, but yes, you can do that right now. Make that a model parameter. So basically, you're specifying the input. So just like the slope tool, you're specifying the input as an elevation data set. It's going to run this through and it's going to calculate slope. Sorry, didn't mean to cut you off. There's a slight delay. So anyway, go ahead.
I was just saying I'd send that to your
Okay.
USM email.
Yep.
Is that your preferred email for communications? Or is it,
They go the same place. I mean, I use Gmail to actually do stuff, but I mean, I use Gmail to collect them, but the USM email just goes into Gmail. I started along. Now they have Outlook online, so I probably could use that just fine, but. I signed up for Gmail like 14. I was one of the first people to sign up for it. So, all right. Let's say week 5. Paste. Yeah, that does look like it should work. Let me try it.
When I select weighted, I get a red X that says weighted error or what have you until I put in a kernel file. When I put in a kernel file, it's all good.
Yeah, that makes sense.
But it just, for some reason, it's not right.
Yeah, everybody gets that little red X that you just mentioned. It ran for me using that one. Anybody else on the coast having a problem getting that to run?
I think maybe I have some sort of setting or something cut off. Because I've looked at Maggie's and what you had up on the screen, and they're exactly the same.
What does your error say?
Let me hang on. I'm starting fresh again. It said something along the lines of weighted mass error and a couple syntax errors. Hang on, this won't take a second.
I had to bring.
Sometimes ArcGIS does have a problem with you using a file, and then if you use a file, you operate on it. ArcGIS has a problem refreshing. Like it says, oh, that file's already in my memory. I already know what that file says. And so it doesn't reopen the file. So it's possible that if you're getting the same error message both times, even though you change the text file name, that it's not refreshing or going to that new file. So perhaps you could try renaming it and rerunning it. And then it would get.
I have an issue saving it. I had to get rid of the star.txt for it to save, but it did save as a text file, so that might have. So I was
Well, the file you sent to me had a .txt.
I think Ian, I'm gonna change something how I saved it. He just pointed something out.
But really, that's the only variable. I mean, the elevation data set, as long as it's coming up, is the other variable, which is we know is not the problem. The only thing that it could be at this point is something's up with that text file on your end, because the one you sent me works. Yeah, or the software is having a bad day, which could happen too. But all right. So what we need to do now is divide both of these outputs by a number that represents. So this is 80. How do you think? Okay, we actually discussed how we got this number right here, 20. Right? That's 2 times the cell size because we're going from here to here, and this is 10, and this is 10. So why is this number 80? Can anybody figure out why that number would be 80?
Exploit all the other surrounding cells. Yeah. Multiply by
So it's all the surrounding cells, 1, 2, 3, but actually this distance isn't 10.
Oh, 9 times 20? Okay.
All right, so let's say that that I was going to give an exam in this class. Well, I am going to give an exam. Let's say I was going to give 3 exams in this class. So I was going to give 3 exams in the class, but I'm going to weight the final exam twice as much. How could I do that? Like what would be the math to actually weight the final exam double the other 2 exams? So in other words, the exam 1 gets weighted 1, exam 2 gets related 1, and exam 3 gets weighted twice. Yeah. So one way to do the math is to just put that test in twice. So in other words, I have a test 1 grade, a test 2 grade, and then 2 test 3 grades. And then I add them all up. What would I divide by? 4, right? Because I'd be adding this test, and double this test. So I have to divide it by 4 because there's really 4 test grades, right? So that is actually the exact same thing that's happening here. Because we're calculating this one, and we're double counting this one. We're counting it twice. We're doing the same thing over here. So that's why this is 80, because this distance is 20, this distance is 20, and this distance is also 20, but we're counting it twice. So it's 80. So that's why we did it over here too. It's always going to be the same number. So what we're doing is finding out the average slope in this direction and the average slope in this direction. But we're double weighting the side. Why are we double weighting the middle one? I mean, really, it's just because whoever invented this thing thought it would be a good idea and probably went out and tested it and decided that it was a good idea because these cells that are closer to it probably have more influence on the actual slope than these 2 cells that aren't really passing through this value at all. Okay? All right. So we're not going to divide it by 80, are we? Because this 80 we decided represents basically 4 times the cell size times 2. So the cell size is 10, multiply that by 4, double that is 80. Okay? So what are we going to do? Not 80, what do we need to do? Whatever the cell size is, times 4, times 2, or just, it's 4 times 2 is 8, right? So it's the cell size times 8. Anybody know what the cell size is? How do we figure out the cell size? Yeah, it's in the metadata for the layer. We can right click on Laguna Beach elevation, look at the properties, general source. Cell size is actually 2. Another thing that I forgot to mention is that it is really, really important very important, that when you start doing any of these calculations, that you make sure that the cell size dimension is in the same units as the elevation dimension. And I already did that. But you need to make sure. That's one of the biggest mistakes I see, because there's so many data sets where the cell sizes are in meters in the United States, unfortunately. Cell sizes are in meters and the elevation is in feet. Okay? Or vice versa, but more often I see cell size in meters, elevation in feet. The other thing that I see a lot is cell size in degrees, because it's just latitude, longitude, and then the elevation in some other. But if you calculate slope on a data set like that, you'll immediately go, whoa, everything's like really flat. I mean, or everything's really, really steep. Okay, it's easy to tell that. But if the units are just feet and meters, you won't tell right off, because what you've done is if the distance units are meters and the height is in feet, you just kind of dampened everything, made it about 3 times lower slopes than they should be. It's not as apparent. Okay. All right, everything's in meters here. So these are meters, elevations in meters. I went with the international standard for today's lab instead of making everything feet. So cell size is 2 meters. Adam, how did that turn out? Did you get it to work?
Still no luck. I resaved it, changed it.
Did you save it as
I moved out. What? Sorry.
Did you save it as a different file name altogether? And try
Yes,
it
sir. I changed it 2 or 3 times to something different. Trying to remember exactly what the syntax said last time. It said something about grid to grid syntax error. I have a syntax error, something about grid placement syntax error, and then weighted, something about weighted, so weight had an error. The kernel itself.
Yeah.
I don't know, because I'm actually wondering if my art map's acting funny. I just opened Lab 4 up, and I can't open my models and editors. So something must be going on with my art map.
Interesting.
I'm probably going to restart my computer, but I'm tracking on how to get to that.
Okay.
I lost my paste file.
Yeah, and I can forward this model once I get it all done. I can post it. Okay, so we have to multiply each of these. What was the cell size?
2.
2. 2 times 8 is what?
4.
4. Yep. So we just multiply this by 4. Oh, 2 times 8? 16, yeah. All right, so we could do that as a multiplication problem if we wanted to.
Why are we multiplying by 4 again?
We're multiplying by 2 times, it's not 4, I just repeated that. It's 2 times 8.
16.
16, yep, so it's 16. Why are we multiplying by 16? Well, that gets back to that test analogy I just said. So it's this distance plus this distance plus 2 of these distances. So that's 1, 2, 3, 4. So we do the cell size times 4. 2 times the cell size. 2 times the cell size. Yeah. And the cell size, and so that's 16. All right. And then we do this math here. So could we put this math into a raster calculator expression? We could, right? This would be pretty easy. This is just a squared, even if there's no square in there, which I think there is, we could just multiply. What's the squaring? Yeah. So we could do that. We could do that. I know there's a square root function in there. And then there's an inverse tangent function, or arctan function, atan function is what's called. All right. So we could do the step of the multiplication independent, or we could just put it all in one raster calculator expression. It doesn't really matter, but since it's just simple math, we might as well. So if I'm going to go like this, I'm going to add a raster calculator expression. Raster calculator. No, that says raster creation. Sorry. Map algebra, raster calculator. Okay, so this is going to be a big raster calculator expression, but we can do that. So these are the outputs here, the Laguna Beach, dx and dy. Now, I explained this before. Let's just review, though. What's the recycle symbol different than the yellow guy?
Yellow was
Layer.
the actual image.
Using a layer that's already been created.
It's using a layer that's loaded into ArcMap. So maybe that's probably what you meant. So if I actually deleted these layers out of here, these would delete. Okay. The recycle symbol means it's from the model. So we actually want to use, it doesn't totally matter, but we want to use the recycle symbols. That way our model is more portable. We're just saying, use the previous step in the model, not these layers over here. Okay. It work either way, but it's really not good practice in this case to use these guys, because these guys are just temporary. I only loaded them in ArcMap to look at them. So it's these ones that we want to use. So I'm going to put both of them down in my raster calculator expression, the dx and the dy. I put them both down there. Make sure there's a little space between them. Let's look at the formula here. So dx is actually first, then dy. All right. So now we're going to build the whole expression. So to each one of these, we need to multiply them by 16. Is it 16? So it's 2. So this would be 2 times 8, basically. That is 2 times 8, 16. Yeah. Okay. Verifying, even though I think that's the third time that we verified it, is 16. What's that? Oh, did you have a question?
Your dx. Yes.
Somebody on the coast have a question? Sorry.
Times 16.
Yeah, don't worry about it.
Times 16.
Okay, so we multiply this by 16, and this by 16. Okay. All right, so all we've done so far is actually create these two terms right here. So now we have to square them, add them together, take the square root, the atan. So there's a little bit of math to build. It's going to be, let's see if there's a function for squaring. Oh, there is this exponent. Wonder what that probably would work. There is one that's just called square though, so let's use that. So I'm going to hit square. Okay. And then do that right there. So I made sure the parentheses are around them, and then those get added together. So I'm squaring both of these and adding them together, and then around the whole thing, I need to square root. Yeah. All right, so far I've gotten to here. I've gotten to there. So I've taken the square root. Raising something to the 0.5 to the 1/2 is the same as taking the square root. This is a refresher from math. Okay, so finally I need to do the atan, the inverse tangent. And that is right here. There we go. Okay, so that's what I probably need to do. Your files may be named something slightly different. By the way, does it matter what order, if the DX or the DY was in a different place here? Just from order of operations rememberings? It doesn't, right? I see some people shaking their head. Because this is an addition sign, and we're squaring them, so we're squaring them, they'll both be positive. So it doesn't really matter which way it goes. Okay, I'll make this bigger. There is one other thing that we need to do, but oh, that didn't work. I could go like this though. So those aren't really on two lines, they're just going over two lines. So the capitalization does matter in raster calculator. All right, the one other thing that we need to do here is that by default this answer is going to come as an angle, but by default that angle is going to be in radians. And so we need to convert radians to degrees if we want to. It's a little easier to understand, I think, for most people. Maybe I'm speaking for myself, but radians are always difficult for me to like wrap my head around, whereas degrees, easy, right? We all can picture in our mind if I say 45 degrees really quickly, and if I say 1 radian or whatever that, I don't know what that is.
Is there a way to make it automatically output 2 degrees?
No. So you need to do the conversion.
So our map will always put out radians.
Well, there are a couple tools that actually will give you the option as part of the tool, but the ATAN tool isn't one of them.
Okay. So all trigonometric functions within raster calculator are by default radian.
I believe that's the case, but I don't know that for sure. But you know,
But at the very least, the arctan it is.
yes. My guess is that they all are, but there are a number of them like that produce that actually have a checkbox. You can say degrees or radians, or even with slope you can check percent, the actual slope tool.
When we do these in the lab, is there a structure order finite kernel tool, or was this how we're going to do it by creating files and notebooks?
This is the third order finite difference that we're doing. The 4 nearest cells, you're just going to modify your kernel so that it looks like the 4 nearest cells one. It's actually a simpler kernel. And all right, so the way that that I do, I think there is a pi function, but I was just typing radians, 2 degrees. It's 57 something. There it is. Times 57, 2958. Technically, it's pi over something, right? Or something over pi. One radian equals 180 divided by pi. So let's see if there's a pi constant. ArcGIS pi. Now that's using it in Python. But I don't know if there's a pi constant. But we're carrying it out to a lot of decimal places, so this should be fine. 4. Let's see if we can get it higher. 180. Well, I wonder if there we could get more decimal places doing that. I mean, everybody here knows that pi is like goes on forever. Right? People, they have contests on memorizing pi out to X number of decimal places. So this number will go on forever. But we're dealing with degrees, and so even if we only did what I originally had, 4, we're going to get a number that's out to the 10,000th of a degree in your slope. So now we're going out to 10,000, 100,000, million. Yeah, we're getting like in billionths of a degree. So it doesn't really matter. I have 295779531. Okay, I'm going to save this in the same directory and just call this slope, or Laguna Beach slope. Yeah.
The description of my error says there is a problem with the kernel file being used to define the weight neighborhood. The kernel file must be a C2 text file, which it is, and it must be saved as a text file, which it is. So it's just saying to check the documentation and make sure the weight kernel file is valid.
Yeah, because you sent it to me and it ran on my computer. So it definitely is a text file. Now, are you sure you sent me the same file? Because now you said.
Yes, sir.
Okay.
Well, I mean, I've modified it 2 or 3 times, changing how I say what I saved it as and so forth, but it's exactly the same now as you had. So, because I keep trying it different ways, it's the same error.
Did you?
I had it saved in the same spot and everything, so.
I didn't dare to search.
Something's wrong. That's. Oh, no. Sorry. I was looking at the wrong one. I was looking at the original one and thinking, oh, the highest slope is 312. I messed up. So I didn't. The highest slope is almost 90 degrees. You'll never get a slope above 90 degrees. In fact, you'll never actually get a 90 degree slope. Anybody think about why you'll never get a 90 degree slope? You're never going to get a 90 degree slope. Even though 90 degree slopes exist in nature, why don't they exist in raster slope calculations? Right, and how are we calculating slope? They're never right on top of each other. We're always calculating slope as the average slope between 2 times the cell size. So the smallest run is 2 times the cell size. So even if the rise is infinity, it's never going to get quite to 90. It's all going to be almost 90. And in this situation, we have some like that. All right, Adam.
I'm gonna do it right now.
Okay. Anybody? Let's see. Did you try moving to a different computer?
I think mine's gonna run.
Is it just you and Maggie today, or is somebody else there?
Me, Maggie, and Jordan.
Oh, okay. It's kind of dark. Everybody, anybody else down there?
Maybe you have to add
What happened?
it just said that I have a problem.
Yeah.
I'm trying to see, do you think I need to have a parenthesis here?
Probably not. I didn't, and it worked.
Yeah, mine didn't work.
Make that bigger, make it bigger.
Cell cells is 2 times.
Go
Like it says, for
Yeah.
your neighbors.
ahead. So it is in your expression. Yeah. Okay, close down. Double click on that.
Assume that this is 3.
Did you type this in manually, or did you just click it?
Like, it's possible.
Yeah.
So what I would
It
do,
would be like,
what I would do if this was my problem, is that I would like start small.
It's like an
So,
overview. So
I
we
should
should do one picture for the 2 cells.
see if that works.
But the middle will go because we're making. I knew you should that one back.
Oh, you're right. I don't.
Yeah, it's like
You know what version of Notepad you run, Dr. Raver?
I just whatever comes with Windows. I can look real quick.
It's not, it's probably,
Do you want me to send you my file and see if it works for you? We can do that. That might be a good thing. Which one was it?
maybe I have a problem trying to get up here.
It's definitely syntax.
I always mess up the syntax. Okay, I just drew in those. Presentation. No, it's. What is that? Thank you.
I mean, delete the output.
Because they're trying to run.
Figure out what it's asking
I did the
now.
box way right.
Ask one. 3 goes along, using 4.
So. Yeah.
Basically all cells in the middle.
Yeah, it can
We
be.
go back and forth.
Did yours work?
This one actually it's double. So we're 2 by 2. 2 by 2 cells. So 2 times 4 because that's double. Times. It's 2 times 4 is 8.
Okay.
Times 2 is 16.
Not showing up.
That's what we're applying it. That's what this formula is.
All right, Adam, you want me to send you my file?
yes, sir, I can't, I mean, I've used Google tips, tricks, everything. I got another question, I'm not too concerned about, worst case scenario, we'll go back and re-put the lab up to where I'm at, so I'm good for practice, but, in lab 4, I had none of those last 2 steps, and for some reason, I can't open my monitor edit. I can open, double click it, open it and run, but right click it, select edit, it won't even
pop up.
Yeah, it sounds like. I mean, it sounds like there's something wrong with the computer then, right? If it doesn't, I'll let you bring it up.
Yeah, I mean, yeah, it does sound like this. I'm having this issue, that issue.
The last one that we saw on this.
All right, I just sent you my kernel file.
All right,
So you can look at what the cell sounds into, like the source, it tells you to like here. And then you just double that times 4. Oh, wait, yeah, we have done this. It's better moving bill budget, but half-time
That looks good.
class and. Yeah, that's it. I'm sorry, I didn't know you were typing.
It's usually not ready to run.
You're paying for that out. Yeah, that's
Looks like that.
Yeah. It's just like. Oh, I think
Yeah, she sent her, she sent this up to me. That's why I'm wondering if it's just your friend.
Well, now
so
these
it's not a
are-
text file that we can read and follow on.
No,
Because I actually. No, I'm just kidding. I'm able to delete the output.
no luck, same errors. I'm wondering, do you think it has anything to do with the path it's having to go through? But it's saved with all my lab 5 or 4, whatever we're doing right now.
Yeah, it's puzzling. So I don't know why, but if your lab 4 doesn't even open, that's a problem too.
Well, it's opening, it's just I'm not able to open my lab 4 model. So,
Right.
Is that?
Yeah, you remember that they have
Well,
second environment. I actually have to run it
Yeah.
from the outside. Right, so we just do a.
Using this as the text document.
The operation, we see what happens. Running outside. Like, just to take the. Because these roles are.
Transfer. Okay. For you all.
Here. You said this one right there, the one
We
that's.
all goes and stick up at 0, -1, 0. And this is both set. It's
Yeah,
so
that's the whole
sad.
problem. None of the problem wasn't that. We can't put it to infinite views anyways.
Because I always touch my environmental folder, but I actually had to read all of the
That's what it
lab
is.
because for some reason my two focus statistics, my two outputs from here, which disappeared that fast.
Yeah.
I'm sorry.
The clearing was,
Can you help
I don't know.
That was your vision, I mean, that's what I ran.
What's that?
It's like it means, the Laguna Beach slope is wide.
Yeah. That's what I'm guessing.
No, you're good.
Okay. It's just black.
Yeah.
But what's the lowest value you get for slope?
Zero.
So you just complete, what's the lowest value you got for slope? The highest one should be
here.
almost negative, probably almost 89.
Highest value is 89.99, my lowest is 27.
Your low is 0.
That's 27.5.
Okay, yeah, that's what hers is too.
And y'all both have a box.
You guys, I don't know.
So, I'm trying this. Is anybody else's ran successfully down there, Adam?
Everybody else.
So
We'll
Adam,
go call. If not, I'll just have to do this lab on the desktop here. I try to do it on my laptop because I have so many issues going from one computer to the other.
let's look at, let's make sure these ranges are the same. Okay, look at those ranges. Are these ranges the same for you? Okay, so there was probably some issue creating those. Are either of the same? Like, is your dy the same or your dx? Or are they both different?
Is this our range over there?
Yeah. This is the break. Let's meet back in about 10 minutes.
My dx is the same. So my dy is different. And then there must be a problem in,
So it wasn't like DY5.
In your dy?
if there's a problem in the text file.
Weird. Can you send us the text file for the DY? Yours?
Yeah.
Because that's the same problem I'm having. I do have.
Log in.
Oh, you had 12 in the dy.
You did?
On my DY?
Yeah.
Oh. And then what is supposed to be in the one? Or two?
It should be 121.
It's just different.
Aggie,
That's the one.
That's why it's not.
Yeah, I didn't check it though.
We all just think you're right now. Oh, you. It's on my phone, I'm sorry. Guys. It just, that you did. I really have time.
Yeah.
So you have to run your focus specifics for UI.
Right.
Yeah.
Where's the thing where I had a file? It's like gone. So did we figure out all the things with the kernels? Should I upload the kernels still?
It was my GHY tag file. Right now it's on.
Can I see your battery again?
For the kernel or for?
For your high and low battery. Like on your
No.
20.
The load should be 0.
Yeah, that's right. I have it.
Okay.
Now here's how to change this. For some reason, I cannot rewrite my files, although it is on the my new policy documents asking to rewrite. So every time I have to change something, I have to change the number of my output.
Because it will rewrite.
And then name, yeah. So I think now it works. Did you get it? I didn't do it in one swing. Oh, I didn't actually display.
Did you make,
It isn't. It is supposed to be good. Right?
yeah.
Nice. I mean, it looks, this really works.
This is why.
89 roll is clear now.
No, I should have checked. I should have checked that I was behind.
No, I knew it was weird because when I ran my my GHY, I look at it and it looked just like the elevation one. Wow. It just looked super similar. So like this is wrong. But
They were.
I gotta keep running my model, and then I'll come and change it.
Yeah.
And then I had a thing where I saw Limbo, and it was just like exploding.
Yeah, no, I was having, yeah, it was about to get real there for you.
So we do change. I don't multitask very well, guys. So when I talk,
either.
I don't really type right.
When I asked you for that, like, I was about ready to just leave, because I was having 5 minutes with her.
And
I was like, that's it, I'm done. I'm done.
And that's why I'm like,
I don't
I'll
think
send
you
you
got
the email.
Okay.
But it's just like I really don't multitask. It's just a horrible thing.
I need to get.
You have to really get back to I feel so bad. Yeah. Oh, it's the new difference in text. Yeah, he did.
No, it came down to the soil.
I don't know where you are. It is useful. Yeah.
Yeah, I like the class, I'm glad I'm taking it because it like gives me a better understanding. But
You're gonna have to report tax books when you have to actually work with it.
well, no, like the guy who does it, never say his name
Right.
He's really cool the way he breaks it down. He really answers all the technical stuff that he's like, and he kind of breaks it down. Beautiful. I don't know my things,
But how much? I would never be able to take it outside of class. Because it's amazing. It's like already learning something that I haven't learned and already doing something that I'm not. So it's changed drastically.
I'm gonna mess with it. Carlton's on his way, so yeah, he's on some things to try.
Alright, I made up the ride, you have eggs, try eggs first.
Yeah, I've done both. It's like, like, two, 4, 5 hours. I've tried.
Not the whole thing.
Yeah.
But just remind me that.
And we were gonna say like,
And then I have to go.
we don't take the half of my.
Yeah.
Well, also,
That's how-
And you know.
This.
I have to figure that out. I
Wait, alright.
started ringing
Oh,
there, but I love it. Yeah, I got mine. Yeah, but that's what oil, yeah, when I got it,
Are you doing, are you guys doing the last like, past like, this is how many
That's good spot.
Oh, yeah, you have to
We
do
still
like-
use the same number.
And whatever.
Like, you can
Constant
do
one. We have to see, like, for sure.
So, yeah, well,
That's like number.
yeah, so I had to close it down, I just deleted the one. When I put it back up, one did everything.
Yeah. I took the voice out to like around. They're getting some.
But I don't say super high level, because you can't get one time.
That's,
No, that one I reached.
yeah, we closed it now.
That one I ever rented file, not sure.
Well, I mean.
Jar to that.
Sorry.
Ellen, you just saved my life. That was kind
Oh, is that?
I think that it's got some macro growth somewhere out here, probably can save them. Save the last.
I mean, I'm learning. I don't know.
Where you are. And you could, anytime. Oh, wait, you can like make a picture of like, for you, and then yours, extra years. And then you can like. There are people here, it's super, and they put their picture.
Right, all of them.
Yeah, so let's see, this one.
It's a recorded picture. Still helpful, we got into the last. I forgot that you're supposed to wrap it.
Yeah, but I mean, for some reason, I'm not going to this fail.
You're like, I kind of fall on my own.
So,
Ellen, you saved my life.
You know what?
Let's take off after display.
What's it?
Take that very wholesome. Yeah.
Because I just started like, this is it, like, I'm not doing it.
You remember that Steve text?
For X, trees. Yeah. Yeah.
Three space three. Negative 2.
I don't even know what I
some
read
reason.
it so I can see it better.
Hang on, I'm gonna just skip this one. This one's the run on this computer.
All right.
You're gonna have your X calculation, or not this.
So what's the,
Just have one output, one is your X output and one is your Y. Right.
what's the prognosis down there?
Carlton is on his way.
What's Carlton gonna do?
He's just gonna check out my laptop and recommend whether I reinstall. He suggested to just make sure I can run it on the desktop here. So I'm going through the steps. I'm about to see if it runs.
So is it, it's your laptop that's having this issue?
Yeah, I've been trying to stick to my laptop because I keep having so much trouble doing a little on the jump drive and taking it home. So
Right. I mean, that makes sense.
yeah, but I mean, if I got to work it out here all the time, I just
What version is it running now?
on my laptop.
Yeah.
The new 10.5, I think.
Okay. I'm not.
Whatever.
Do you have? I mean, you have Spatial Analyst turned on and all that stuff, right?
Yes, sir.
Okay.
Yeah, the two problems other than the notepad files coming in and my model and lab 4 not reopening to edit, so he's going to see if he can figure it out. If not, I'm going to uninstall, reinstall, or hope for the best.
Okay. I'm just gonna step out for like a few. I didn't leave, so I'm just gonna step out for like 3 minutes to go to the restroom. Is there anything you'd like me to leave up here? That'd be fine. Okay. So remember that your text, the names of your file are going to be different. Okay. I'll be right back, and then we'll continue on. We'll talk about aspect, yield shape, and then I'll talk about what we're going to do for the lab.
After you
I don't want to mess up your model any more than.
I'll plug everything into that. So that's it, it's me. Yeah.
You got to let this.
Make the model raster, get the raster. You don't need that particular raster.
I'm just trying to see, like, what is so different between mine, like, compared to yours and what yours was. That's my good. This is for the second, fourth. 3300. Bigger than 1 0. I have some.
He's in my soils class.
She's not supposed to be, but she's in the class.
It is always the same.
Where Alvin's store is, and I got it saying it's in auto, but I wonder why it goes all past.
Because mine is exactly like yours.
Yeah.
Repair your dad's space.
I'm supposed to have a fancy class.
Oh.
Oh,
See,
that's-
like,
Like,
it is getting better.
so you got any work?
I say mine's my
You need
username
to get her the biggest.
slash document slash RGS. I named it like nearest.
So
Like
you take the output and your Y output, put it
She's
in the rest.
thinking.
I'm doing the Y now. Okay.
Because that's saved into your database
The output's going to be in the database.
All right, Jordan, you got that Y in?
Where it's going from.
3, space 3.
Enter. Once you want. Enter. 0, 0, 0.
Yeah.
Enter. -1, -2.
Maybe because it is saving it to a database and you're already putting in the database file.
Mostly for stuff like that.
What was the matter with it? See, mine doesn't hurt, so I don't understand. That's one of the.
That makes sense. Dr. Parsons. You know exactly what she said. Something about making I hate this so much. Hospital and
What to do now?
oh. That's what.
Yeah. We're like, just kind of trying to figure something out.
Alright.
This is what did you do the rasher calculator?
We'll see what I can figure out.
This is what you told me to put it like the one that we saw on the slide, so that's, I typed it like that. Except I took our nearest X of the one that we just did and our nearest Y of the one of the text document that we did. And then I did the times 4. Times.
Yep. But it has a value.
What I did was I just
So, yeah, fuzz on them.
Yeah, that's what I did.
Go into the range calculator.
might be elements.
Concept, what are we trying to calculate? Parameter calculate, send it out. So you got add it. Now, we can say that. Times 16. Plus 5. Square. Square. So, I think that's ultimately. That's what.
What does that mean?
I don't know what that means.
Hang on, I'll actually look. Okay, so I took that one, that was my second one. My second one, and my second one. And then 4, and then 4.
Oh, you're right.
And you think?
What are your things?
You're
We got time to say.
parentheses.
Police are
I think the last calculator.
and homes leading into fish.
One right there.
You're became, you're one here.
No, it's you did it.
Yes.
So every time, and then that's it, right?
Oh, yeah. Doing something to
And now it's like something to repeat it. Where you think?
Oh, mine was off to like the
Yeah,
same
it's like
section.
8.9.
I should not be thinking of that. Oh my God. I'm saying,
got a question.
I had like a couple meetings for coffee after, before conference class.
It's first semester, that's first
So I went to his class and talked to him in his class. So I'm just basically sitting there, and I didn't have, I had like,
This one looks more fun.
yeah. So yesterday I was pretty much, we made up coffee, but at the same time, my mind was like, so I'm trying really hard to think. Because of all the things and everything, it's not taking you double and I really like the reading and everything. Yeah.
So this one's definitely dark.
This currently produce this.
Color?
You got, like, written down, and I'm not sure. Maybe. I don't know how they try to do it.
The one that's lighter. It shows all the ones like times 4 or times like 16 that are all mirrors. That's more valuable. Oh my gosh. Elevation. Whereas the home one, just like 4 that we did.
But I went home and I
less of a mirror.
Yeah, she might be. It goes down through the
Because this is more lighter, but this one's wider. This one does like double whatever that is.
that's all the same thing.
I kind of like
My dad was passing my work and I had like very intense class.
Hey, Dr. Ray.
Yeah.
Can you go back to St. Andrew and take a quick picture of it?
This one?
Yes, sir. Thank you. I'm working on the guys' topic.
Remember that you need to do that too. So that's the full syntax.
Thursday, Friday, Saturday, Sunday, 4 3 days. So I can come out and go to school, I can stay home, or whatever, if I needed to like go home, and if I needed to travel home, I have 4 days to do that. Whereas if my classes were spread out all week, no, that's fine.
That's what I'm telling you. It sounds good because you have the Thursday and Friday,
But
but
if
you
I-
don't actually have to get.
But if I had to, if I absolutely had to, I would do that. But otherwise, I have 4 solid days that I can just like,
Change the water,
you know, like.
All right, did you get it down?
Yes, sir, please.
Okay. So what we're going to do here is continue on. We've done slope. Now we're going to talk about aspect. Okay. So the aspect is the compass orientation of the slope. So what that means is that if you are standing in in the center of a particular cell, what we're trying to model is the direction that that slope is going in. Now, in mathematical terms, facing east is 0. Like on a Cartesian coordinate, facing east is 0, but ArcGIS does the math for you and makes it so that facing north is 0. And it goes around from there, right? So by default, this is actually going to give you that mathematical version there. Okay, so what it does is says, okay, the direction, the difference in the y direction versus the difference in the x direction. Okay, so these are just the same kernels that we've been dealing with before. but the formula is different. Instead of adding them together, we're dividing them. We're not squaring them, so that order does matter. And then we're multiplying it by -1, or just turning it into a negative, multiplying by -1. And then same thing, use the ATAN, and you'll get that number. And obviously, if you're doing this in ArcGIS, which you will be doing for the lab, you need to multiply that by the 57 whatever to get the number in degrees. All right, so we could calculate it both using the nearest 4 or the nearest 8. These represent the kernel math right there. All right, so one problem is that what if this number results in a 0? In other words, what if there's no difference in the x direction at all? There's no difference in the x direction? How's that? What's going to happen in the math? Right. It's going to be undefined. And so ArcGIS takes care of that for you. What it does is areas with flat slope, in other words, totally flat areas, they're coded as -1 in ArcGIS. Right? But in your manual calculation of it, it may be that you get some no data cells. I actually have not calculated it quite yet, but if you get no data cells, which is possible, that's why. And you could put a conditional statement in to replicate exactly what ArcGIS produces. So in other words, you get degrees unless that direction is undefined. Why is it undefined? Well, if the slope really is 0, then there is no aspect. It really is undefined. There's no direction of the slope if it's not. So it makes the math actually makes sense. It produces an undefined value because it isn't defined. But it's just like the slope of a line that is, in Cartesian space, because we're using Cartesian math to do this. So, yeah, all right. It goes from 0 to 90 to 180 to 270, all the way to 360. So those are the directions. In Cartesian math, it actually is the opposite. This is considered 0, 90, all the way around, but it starts this direction. It's like kind of. All right. There's a few other derivatives that we'll talk about how they're created. Now, viewshed. Who's done a viewshed before? Nobody. Okay. So a viewshed calculates the area in a raster elevation data set that is visible from a certain location. So you'll get, depending on the software, you may get 1s and 0s, or you may get 1s and no datas. But in any cases, the 1s will represent that cell is visible from an observer. So how does it calculate this? Well, it's a very simple but intensive process. Basically, all it does is draw a line to every cell, and it figures out if this line intersects with if it intersects with anything in front of it. So it goes to this cell, if the cell's right here, and figures out if it hits it, and if it hits something in between, it's not visible. If it hits something, but it still goes cell by cell. So it's really like a local operation, but it in fact basically draws a line back using just trigonometry. Now ArcGIS added in 10.5, they added the ability to actually compute this knowing that the Earth's surface is round. But there's really very little difference in that. But over a long way, like over the United States, that could be important. But anyway, there is, just so you know, there's two visibility tools, and one of them's called, one of them's actually called something like visibility for the whole Earth, or around. So they're all under surface. Yes. So actually, it's just called Viewshed 2, I believe. Yes. So it uses geodetic methods, meaning that it actually accounts for the shape of the Earth being round rather than using the projected coordinate system. Okay.
The only difference then between the two, between you said and you said two.
I think so. The description makes it sound like that's the only difference. It does look like there's some other parameters. But I've never used, honestly, I haven't used Viewshed 2. It's a relatively new addition to the process. So
that would be what a person on the ground can see, or field of view, this working area in your ration.
that's a good question. So yes, it's as if the person is on the ground, or you can actually add a Z factor. So you can say that the observer is higher than the ground. Okay? Like if they're on a platform or a pedestal. But there's applications for this, like, it's called a viewshed. One of the applications is actually planning, like vistas. But there are things that work a lot better, like radio transmission signals, if they are sight-lined. So you could use a few different locations to try to find the best place for a radio tower. What could be seen from this radio tower in terms of where it was on the surface of the Earth? One time at a conference, I actually saw somebody, they were from the military, that used the Viewshed tool as a input to their algorithm for scouting where, like, a possible attack could come from a road. So what they did was they ran the Viewshed tool over and over again, every 10 meters along a road. And then they overlaid all of those. And so the higher values were areas where they could see more of the road. So, because the output says, yes, if I can see it, no, if I can't see it. And so everywhere along the road, I run it, and I have ones and zeros. Ones represent I can see that position. So the value, the area with the highest value, let's say it's got a value of 32, and I checked 100 different spots along the road, that means that it could see 32 of those spots. If it only had a value of 1 or 2, it could only see 1 or 2 positions on the road. And so you could use that to say, these are the spots where an observer watching the tanks move along the road could see the most part of the road. And these are the spots where they could see the least. So they would most likely pick the areas where they could see more of the road if they were trying to ambush the tanks or whatnot. So that was another application, but that's what Viewshed does. Okay. Visible or not visible is what you get. So the output, this is actually the output draped on top of a DEM. So the visible areas are white. So those areas are visible from this viewpoint. Anything that's dark where you can still see, you just see the shaded relief, those areas are not visible from this viewpoint.
we add the canopy to that?
The canopy?
Yeah, like the,
Yeah, well, you could use a digital surface model if you wanted to, instead of a digital elevation model. So, like if you use if you use a digital surface model, actually the elevation of all the trees, then it would show you different things being available, right? And you can also add a height, a z factor to the observer. So you could say the observer is 10 feet off the ground, and then you would get a different answer as well. Those are both options in the viewshed tool. So it is a simple algorithm, but it's a long process because it has to calculate from every cell. It has to calculate the triangle back to that cell and see if it hits any other cell, then it's not visible. So it goes from cell to cell, calculating the triangle and whether or not it intersects the surface. All right, the final thing we're going to talk about today is hill shading. Okay, hill shading, it actually computes the surface of illumination. So it's computing how bright a cell would be based on its slope and direction. So if it's facing right back into the sun, it would be brighter than if it was facing away from the sun. Okay, then it won't be bright. It'll be dark. It'll be in a shadow, like that. Okay, so this can be very useful for two purposes. I'm going to go ahead and calculate it really quick in ArcGIS because one of the purposes for the cartographic is for cartography. So it's under hill shade. And I'm just going to input the Long Beach elevation raster. And I'm going to leave the defaults and say OK. And it's going to run through here. Okay. And you can see that those values, they actually, I'm going to zoom in right here. They actually do a better job, I think, and lots of people think, at giving you an understanding of the surface than the elevation itself. Like here's the elevation itself, here's the hillshade. What kind of features can we see in the hillshade that were really hard to see in the elevation data itself? What's that? Yeah, you can see the values. What's that? Values? What's that, Adam?
Canyons?
Yeah, you can see the canyons, valleys. You can see these all these homes that are terraced. You can see that the slope is. I mean, you can see that the hillside has been terraced. Like they cut the street to make it flat, and then they cut the next street to make it flat. So you can see this whole area where they flattened it for the school. This is the top of the world school I was talking about before. So you can see they've cut that area to be flat. Going back towards the beach, you can see more terraces, and so on. Interestingly, the default value that it chooses is having the sun shine this direction. So the default value was like something like 345. So on that compass angle from 0 all the way to 345, the sun is shining from the northwest. Okay. Does the sun ever shine from the northwest here in the United States? No, not even in Southern California, which is about the same latitude we are right now. The sun never shines from the northwest here or in Southern California. However, for cartographic purposes, people have noted that this actually does a better job at really showing things. Like this is a ridge line. See this road? It comes down. We can see that that's a ridge line, and as it comes down, actually, my dad's house is like somewhere right around here. It comes down here, and we can see that this is flat. This is the high school, not the junior high. If we were to look at this exact same area though and change this so that the sun was coming like out of, well, let's just do the opposite direction. So that would be 90, maybe 100. And change it, because the sun really could come out of the south. Oops. But that does happen. That'd be like in the middle of winter. Well, actually, just during the day. Okay. Elevation. Need to make sure I choose elevation. I'm going to say okay. So now I'm making the sun come out of the south. And most people, when they look at this, they would say, oh, this is a ridgeline right here, isn't it? They would say that's a ridgeline and that's a ridgeline. But really, now the sun's coming out of the south. So this is bright and this is dark. So this right here is actually the ridgeline, the same ridgeline that we saw previous. See this ridgeline right here? It's much easier for most people to interpret that as a ridgeline. You know, some people hypothesize it's because, you know, we learn to read from right to left and down. And so we see, when because this isn't real, right? This is just shadows on light on a page. And so when we see this light area here and a dark area here, we interpret the light, for some reason, we expect the light to be coming out of the top right corner. And so we see it as, we see this one as this light is coming from the top right corner. We view it as a ridgeline when in fact that's a valley. We're looking at the light coming this way, and it's hitting the side of this ridge, lighting that up. And so this view is considered cartographically more intuitive. So if you're making this for cartographic purposes, then you use that one. So when creating a cartographic hillside, you place the light source in the northwest. So there's two different parameters here that you can change. One is called the altitude of the sun, the altitude of the light source, the virtual sun. And then the other one is the azimuth, the direction of the sun. Okay, so those are the two things. Now, the other purpose besides cartography, and cartography does get used a lot. People put, one of the nice things you can do, so I'll get to the other purpose in a second here, but one of the nice things that you could do is actually, let's say you want to create the elevation data. You want to show elevation, because elevation is actually kind of important for knowing what's high and what's not. I mean, it's hard. In this one, we can see the shape of the earth. We can see that this is bright, right? This is dark. But we can't really see that this right here is actually a little bit higher than this down here, because they're both bright, okay? We can't really tell which one of these is higher. We can kind of judge it, but this one's lower because it's further down the canyon, but it's hard to tell. So what if we wanted to mix the two so that we could actually see the shape of objects and the height? Well, we could take this Laguna Beach elevation data set and change the symbology so that it was, used a few more colors. Let's say something like this. Apply. Let me see what that looks like. Okay, I'm going to invert it so that the blue is the lowest area, because I think that's a little more intuitive. I'm going to zoom. And then finally what we could do is to make it transparent, semi-transparent. That's under display. Transparency, we'll make it like 50. Apply. Okay, so now we have kind of the best of both worlds. We can see the hill shaded effect, plus we can see the elevation effect. So we can see these were the two areas I was comparing. We can see that this is yellow and this is kind of yellowish, or sorry, this is yellowish green and this is green, solid green. So this is definitely lower than that. We can see both sets of information. We could put whatever we wanted to on top. I've seen people actually drape the satellite imagery, even though it does by nature contain some of this sort of information. But lots of times the satellite imagery is color balanced, so it gets rid of some of the shadows. And then they put this in there to reinforce where the shadow is coming from. This became such a... What's that?
Will you talk about top layer on and on?
Yeah.
I was just looking at some.
This has become such a popular effect that 3 or 4 versions ago, around 10, they actually added this button here that does this. Use the hillshade effect, and so it calculates hillshade for you. So if I go this back up to 100, or sorry 0, say OK. Now you can kind of see how it does it, but I still don't think it does it as well. Okay? I think that the muted tones of the other data set where this was 50, and then we take off the just use hillshade effect. I think that actually looks pretty pleasing. Okay, so this is a nice cartography trick. And even though they've tried to replicate it as just a single option, it still looks better if you do that. Okay, so finally, cartography is one reason for hill shading. It's a very good reason. However, you could also use hill shading to model the incident light in a particular location. So if we were trying to build a model of where certain things grow, we could use that model we could use the hill shading to come up with a model as to what was getting light. And in that case, we would want to try to approximate the real position of the sun at a certain time period. Or if we wanted to model, hey, we're going to have an outdoor meeting. What areas are going to be lit bright and lit up? What areas are going to be dark? So there's other reasons for including it in a model. So you use real sun positions when you're doing what we call analytical hill shades. So here's a shade. We can do it on all different scales. Here's a shaded relief of the western United States. Would this be considered an analytical hill shade or a cartographic hill shade? It's kind of hard to tell right off, but if you know about the West, right, the sun is coming from this angle, so that's not natural. Yeah, this is it's cartographic hill shade. All right, now this is mostly for the lab. This is the formula for a hill shade. The formula for a hill shade is not that difficult. Okay, it just involves some numbers. So we can actually feed this into a raster calculator expression, the whole thing. There's a few little tricks though, okay, but they're not big tricks. First of all, it wants everything in radians, okay, which ArcGIS, when you calculate slope, you only have the choice between degrees and percent. So you have to change it. So if you calculate slope, you have to change it from radians. The other thing is that this formula, I don't know why it's expressed like this, but it's expressed as zenith, which is actually defined as 90 minus the altitude. So if the altitude of the sun is 45, then it's 45, right? 90 minus 45. But if the altitude is 10, then the zenith is actually, what we're looking at is the opposite. It's 80. So it's the angle from, altitude is the angle from the ground to the sun. This is the angle from, well, the opposite angle, sun to the ground, okay? So that just needs to be changed, okay? So the as uses the angular direction from the sun, measured from the north, Okay, that's the azimuth. That's the other one. All right, the azimuth is a little bit tricky because you have to do this math to get to change mathematical direction into compass direction. So in order to get the azimuth that you're going to feed into the formula, you take your compass angle azimuth, 360 minus your compass angle azimuth plus 90. That'll give you the mathematical azimuth, so starting at 0 meaning east. All right. So, however, sometimes that'll give you a number that's greater than 360. So if the number is greater than 360, then you'll have to subtract 360 to get the correct number. So how would we implement this in a raster calculator? Well, first, how do we implement this in raster calculator? Pretty easy, right? Azimuth plus 90 equals 360.
Maybe you can do a column.
Yeah, you could do a con statement. Yep.
If it's greater than,
It's greater than 360, then say the number minus 360. If it's else, use the original number. Okay. Subtracted by 270.
Yeah. Take 90 out of 360.
So you mean here?
Yes. So it's like 270 minus that instead of.
Well, I mean, we could try a number like. I mean, I think it's going to be different. All right. So that's the last. That's the last slideshow. I mean, the last part of the slideshow. So let's talk about what we're going to do for the lab. Actually, I didn't write it in Word. I just cancel. No, I want to view the files. No. Okay. Oops. Canvas. A button somewhere. Okay, so if you go to the lab for today, by the way, I have the reading up, but not the slides up for next week. If you go to the lab for today, oops, that's not it. Lab 5. Okay, this is I'm just gonna copy this and put it in a Word document because it'll be a little bit easier to see.
so it is.
All right, so there's 3 tasks to do. The first task has the most text, but it's actually the easiest one to do because all you're doing here is taking the kernel that you created and modifying it so it does the 4 nearest neighbor kernel. Okay, so you take your kernel, everywhere where there's a 1 or a -1, you put a 0. Everywhere there's a 2, you put what? A 1. Right, everywhere there's a 2, yeah, a 1 or a -1. So you change all the 2s to 1s and you change all the 1s to 0s. What other change has to be made to the formula?
Change the 16 to a 4.
Yes, change the 16 to a 4. See, is that right? Because cell size is 2. Yeah, exactly. So change the 2 to a 4. 16 to a 4, and you're right. You're all done with that. However, there's a little bit more that I'd like you to do. All right, I want you to make a quantitative comparison between each version. So save out the third order finite difference, the one you've already done, and then when you don't write over it, create another one that is the one from the 4 nearest neighbors. Then I want you to make a quantitative comparison between each version and the slope tool output. So then run the slope tool that's in ArcGIS. So you have 3 different versions of slope. The one ArcGIS creates, the third order finite difference, and the 4 nearest neighbors. The 3 versions of slope. How would you, what does a quantitative difference mean? What does a quantitative comparison mean? Yeah, you're comparing the actual numbers. So how could you compare, I mean, there's too many numbers to compare individual numbers. So what are some things that you could do to summarize the differences? One of the things is I put in there a map of the differences, 2 maps. Okay, so what I'm picturing there is that you take the one that ArcGIS produces and subtract the third order finite difference that you created, and then take the one that ArcGIS created and subtract it from the 4 nearest neighbors. Okay? And then answer the question, where do the larger differences occur? Okay? Do they occur in areas of higher slope, lower slope, whatever? Which version of slope is closest to the tool? And in fact, one of those 2 is the same exact formula that ArcGIS produces. So in that one, you should have very few differences. Now, I recognize that because, depending on which radians conversion we use, it may be slightly off, and the edges might be different because we treated edges differently or something. But one of them is exactly the same, the other one isn't. So you'll find that out. So you need to put those 2 difference maps. One of them is going to be pretty boring. It's probably going to be mostly one color because the differences are almost the same. One of them will be slightly different. You could choose to symbolize that using like standard deviation, so it'll accentuate the differences because it may show up that they're just really close to 0. So turn in your model. All 3 of these you're going to turn your model in. Okay? All right. Now the second one, you could probably take this model that you created, right-click on it, copy it, paste it. You got a new model for calculating aspect. Now for this one, what you're going to do is you're going to open up the model, and you're going to change the raster calculator function. If I was going to do this here, where'd it go? Who knows? The raster calculator function, once you copy and paste it, you're going to change this part, because this is the same. That doesn't change. This will change. Your formula will be a little bit different. It's going to be simpler, because it's not going to have any squares or square roots. It's just going to have 1 divided by the other. Okay? You're going to have to change. You're only going to do this for the third order finite. I think I say it in the lab. Let's make sure I said it in the lab. Kernel compare. Okay, I didn't say. But only do this for the third order finite difference. Okay? So the 16. All right? So compare the output of the aspect tool to verify your work. So use the real aspect tool and compare the differences. If there are any flat areas, totally no slope, those will be differences because, well, they'll all be no datas. But ideally, it should be identical otherwise, or very close to the same with rounding errors. So you'll know that you got the right answer there once your aspect looks the same as the aspect that ArcGIS creates, or really close. Okay? In fact, to get full credit, your aspect has to look exactly the same. In other words, if there are no data values, you need to get rid of them and make them -1 values. You can throw that right into the raster calculator expression. All right.
On that task 2, Dr. Raver.
Yes.
So we're going to just do the math, by hand, and then use it in the aspect tool? That's what I'm not understanding about the way it's written.
Well, you're going to run the aspect tool, and then you're going to run your tool. Sorry, you're going to run the aspect tool, and then you're going to run your tool and compare the results. But yeah, you're just like how we did slope. In fact, let me do this real quick. So we did slope manually. So now I'm going to run slope non-manually. Slope. I'm just going to run this, and I'm going to choose the Laguna Beach elevation. And I'm going to save this as Laguna Beach slope underscore ESRI. I'm going to leave the Z factor on want degrees because I created degrees. And when I run that, the highest value is now 82, 88. My lowest is somewhere around 0. So I know there are some differences already, but I'm going to find the minus, or that's under local. No, it's under math. I'm going to subtract the ESRI, the one I calculated, run it. Those are the differences right there. So the high is 0, the low is negative 89.9862. I can see these are the differences. Where the differences occur, they're occurring mostly in high slope areas. That's what you're going to do with the aspect. You're going to do it once regular and once you could calculate. You're going to do once as a copy of M slope here. Because really, the model is almost identical. The only thing that's different is this raster calculator. When you calculate slope manually, this is the only difference, is that raster calculator expression. And it's going to be this formula right here. And these are just the outputs that you already dealt with. So these two are the focal statistic operations outputs, except for they haven't been divided by the cell size, the appropriate cell size value. So you're going to run aspect like that once. And then finally, the last one is that you're going to replicate the hill shape tool in a model. Okay? So in your model, this one you're going to make altitude and the azimuth parameters that the user can choose from. You're gonna make those parameters so the user can enter those, just like on the regular hill shape. So after calculating slope and aspect on the elevation data set, then you can, after calculating those two, it's possible to do the entire rest of the operation as a single raster calculator expression. In other words, what I'm saying there is that once you calculate slope and aspect, you can put the rest of this in a raster calculator expression. So really, you probably won't need any more tools than, I already closed it, but you'll need to run, there it is. You'll need to run slope and aspect instead of two focals. And you'll need to run slope and then aspect. And then you'll need a raster calculator to put in this expression right here. Okay? So you need to put in that expression. And then once it's done, it should calculate hill shape for you. Let's look at the rest of this text. So, if you use your version of slope and aspect, then basically you get extra points, okay? But if you use ArcGIS's version of slope and aspects, you get full credit. So you get some extra points if you use your versions of slope and aspect, okay? In order to do that, you'll have to make your slope and aspect tools have an input and output parameters. What I mean by that is see how my my elevation is an input? And now I can make this one an output. I can make that a model parameter. Now when I save this, I can open up another, I'm just going to close it too. I can open up a new model, new model, and I can take my model that I created and put it right there. Oh, sorry, I tried to add the wrong one. See, now my M-slope model that I created is here. The input's here, the output's here. I can change those because they're model parameters. So I can make this the elevation, any elevation data set I want. And I can make this be now the input, because now what's this when it finishes?
The output.
Right, it's the output, but what is, it's the slope, right? So it's a slope raster, and I can make this be the input to the big formula that calculates hill shape. Okay. So if you do it this way, so you're going to create an M aspect, an M slope. If you do it this way with your own data, you get extra points. If you use the ArcGIS slope and aspect, you still get full credit. All right. All right. So to finish off, you can do like what I did and make them all in one toolbox. So you have to turn in 3 models, but they can all be a single toolbox. You turn that in. You also turn in the answer to the questions, and then you zip all those items up and upload them. Okay, don't upload the data, just the toolbox and the question, and the answers to the questions, like as a Word document or something, and the maps. Yeah. What's that? It's a TBX. Yes, that's what I need.
And the other day, to know if I should take a print screen.
Right. .tbx. Then I can open it up, and I might have to mess around with the sources, but I've got all the data, so it'll work for me to test it. All right. Okay. Anybody have any questions about what you need to do for the lab?
You know what, Dr.
All right. Go ahead.
This isn't really on the aspect formula and the shape relief formula. Can you just go over what these variables are exactly?
Okay.
I haven't had too much math.
All right. So on the aspect one, it looks like it's math, but it's really not like anything that we haven't already talked about, because the formulas are almost identical for slope and aspect. Okay. So for aspect, the only difference here, so this complicated thing right here is the same complicated thing that was in slope. It's all this. See, dz over dx equals all this. So you already calculated it once. So that's the focal statistics stuff. So this is the focal statistics for the x direction and the focal statistics for the y direction, x and y. That's what these two are.
Okay.
They're the same kernel. That's why I'm saying you just copy and paste the one that you already created, or since it didn't work on your machine, I'll upload it. But this is the output from the y kernel and the output from the x kernel. Does it make sense?
Okay.
Why those would be, in general, does it make sense why those would be, now it matters the order?
Yeah, it's one's on top, one's on bottom.
Yeah, one's on top, one's on bottom of a division. But since we're talking now about, direction in azimuth, it does matter whether you put the x direction or the y direction, because it would be facing a different direction. So anyway, so this is just the way that you actually put this in Raster Calculator is to take the output from the focal statistics in the y direction, the output from the focal statistics in the x direction, divide those Then multiply them by -1. That's the quickest way to make this negative term work. And then just put a tan around the whole thing. And then to turn it into degrees, you have to multiply it by 57 point whatever. Okay. So if I was going to do this really quickly, in fact, I could. Let's go to this formula right here. I'm going to copy and paste it and fix this formula up. I don't need to square anything. I still need remember, I still need to do the divide by right here. Oops. Don't need to do square anymore. Still need to do 1. I don't think I need both of these anymore. So this is the a tan, is going to be the whole thing there. Yep. Okay. Did I get the x and the y right? Nope. So this needs to be y. This needs to be x. And I'll put this on the second line so you can see it. But that, oh, sorry. Oops. Okay. So that is the formula for, that's just like it written in ArcGIS, but that's the same exact thing that's right here. Those are equivalent statements. This is it actually implemented. Remember that your file names will be different. But other than that, it should work. Did I do anything wrong? Anybody see?
Still times 16, right?
Still times 16, yep, because you're going to do the third order finite difference. Yep. Okay, now, so Adam, that's half your question there. So this one right here, what are all the terms here? Well, this one's a little bit bigger. Right there. Put that on a separate line, that on a separate line. Okay, so several of these are the same. You've got the zenith in radians. You got the zenith in radians a few times, right? You've got the azimuth in radians and once. Okay, now the zenith and the azimuth in radians are constants. They're not rasters. They're just not they're constants. They're variables, but they're just rasters. So when you put them, they're just individual numbers. Just like in math terms, they'd be like a scalar. They're just one number. So you can represent them, remember, in ArcGIS by saying I want to create a new variable, and it's gonna. Let's let them. Just because it seemed to work better, let's let them make them doubles. Okay, and you can call this one, call it azimuth. I don't know if I'm spelling it right. Okay, so now I have the azimuth, and when I go to write my raster calculator expression, I just write % azimuth, because that's what I named it, %, and then I can throw this into the formula. But this formula here is actually less complicated because it's just, cosine and sine. There's no output from anything. There's no output from the focal statistics. Now, to get this to actually work in ArcGIS, these have to be capitalized like this. So you might want to do that. There you go. So let's just do the zenith in radians really quick. Okay. So how would we calculate the zenith in radians? Well, remember that the zenith from here is actually 90 minus the altitude. So we would have to write %. I would double click on it when you're in raster calculator, but % azimuth, or sorry, zenith. We haven't even added that one yet. Zenith %. Is it minus 90? No, it's 90 minus. So 90 minus. See that? So we're saying 90 minus the zenith. Now the problem is that this is in degrees. Okay, this number was given in degrees. Or it's altitude. So we want them to give us altitude. We're gonna get zenith. Like that. Okay. So 90 minus the altitude will give us the zenith. Now the problem is that this is in degrees, so we have to put it in radians. So we have to multiply it by radians multiplier. Let's look that up. I want an internet window. There we go. Radians, or degrees to radians. Just go like this. All right, there's the that's what you multiply it by. All right, so that 90 minus the altitude times this number gives you the zenith in radians. So this whole thing, you just repeat that right here, and then you do a similar thing with the azimuth, but you don't have to do this 90 minus stuff. All right. Okay, so if you know, if there are questions as you work through it, ask me. We can even let you know if the questions don't arise until sometime next week. We can spend some time next week talking about questions. You know, like if you work through it and you say, hey, you know, it's either not running. That's a typical one, or I'm not getting an answer that looks right. That's an answer I like a little better because at least it got partway through. So, all right. So I'll leave this screen up for a few minutes because it looks like at least people up here are interested in seeing it. And then we can take another. Well, I need to take another little break. So maybe like 6 minutes. I'll be right back, and then. I can answer more questions, or you can start working through it.
I'm my sister. Well, yeah. That's what that's what we're doing with that. I have two color eyes. That's a cheat. I mean, I've talked to several vets and several
And then we have
that is twice that.
but we have Dr. Miller, and then I have.
Actually, it's funny. Go to the cheeks and action camera. Put a 64, 120. I'm thinking bringing all the digital cameras that just sit in the shelves and fly around. I want to set that tripod up every class.
How long are you gonna do?
That'd be good for me.
Friday? At 10 a.m.?
So yeah, I'll pick it up.
I got
Stop. So there's something interesting about it. Show. It doesn't show. It's like, It's just catastrophic.
Yeah. It's not useful. Well, it doesn't matter how far I was.
Just trying to figure out like why we actually were slow to something.
Yeah, we do that with the level.
Yeah.
You can see like how individual causes the other way.
But it'd be great for me.
Yeah, well, that's why you're using slope and cross. Because it's. The slope.
Might be a copy. I have it if you want it. It's at home. I don't know. It's technically not the right copy. They like the law, but whatever.
Just sit
Yeah.
there.
But, you know, I'm part of the sector. I'll need it back by the time.
Hey, look, see what's sure.
I don't know. I just. I really like.
Yeah, are you okay with tomorrow?
I took it.
Okay.
So like, out to those.
I can leave it. I'll be here tomorrow.
It's such a like, oh, fuck.
I might leave it. And then I'll be
Like everything that I was doing is that I was
And also, I
I might not be here tomorrow. I'll probably, are you gonna,
Tomorrow's Thursday?
Yeah.
I think it was something.
Okay, I'll drop off sometime. Cause I have a church at 9:30. And then I'm expecting my hair to try and do this 11.
Yeah, on Wednesdays.
No, I took a residency a few semesters ago.
Yeah.
You don't need to. I'm here in
Yeah, like,
tomorrow.
Kansas are.
I think we'll take environmental.
That core.
Yeah, I tried to take it this semester after we took residency.
No one signed up for it. I signed up. Oh, he canceled it pretty hard.
Oh, so you didn't have
I remember them telling
Because
me.
he asked me if I could come to the coach, and I was like, I gotta ask him for
Or-
No, your partner's like, we were nice, but like, really, really nice sometimes.
And just like.
You're not, it's not an option now. Students come there, but they're not supposed to go to the coast to pay parties.
Oh, yeah.
Because you're taking classes here. It's like 1 hour, you don't have 1
I'm on
hour,
the coast
2
a
hours.
lot, so it's not that, but I'm on the, like, I have to plan my.
No, he was being nice, trying to make way for you to take the class.
And I appreciate it because I would
Yeah.
rather have taken it that semester than now to have to take a year after I go.
You have software on
I hate to cancel it. But I think, like, you guys enroll for class pretty, like, in the first week before it's to enroll. And then sometimes they don't get the students that take, I'm gonna take the class. The second week, they're like, I'm trying to remember the class.
Yeah, that was like the one semester where I enrolled in early enough in class.
And they cancel, and they cancel the class. We try to take it last semester, and then.
I tried to take it last semester. This semester they didn't offer it. This semester I tried to take that programming class.
Me too,
And
and
I
that's
got dropped.
They said that, that were like,
Oh,
then the program, the Python, now Python is probably in spring. Well, it's programming, but that was, it's like 460.
I don't think it's done. I wanna say.
Yeah, no, baseball program.
Yeah.
Don't try to sign up for any of those, it's yeah, because it's, he's the only one to, OGIS now here on the Hattiesburg side. I hate that the campus and the coast is not so close. And that you guys don't have like, because if every sophomore in geography was in the same page and taking the same classes, they could make a way that they could offer the classes on the coast that would give you an opportunity to drive there. Or because you wouldn't have this window, but they cannot calculate that window because everybody, each student's taking a single class, so it's just. And then they're like, you want to take my car with you? Because I think I would prefer driving down than taking a class on my own. Physically, I can work with this class.
I'd rather do a class, but I don't mind driving to go for a class, but you
No,
can't
but
ask
the
me to do
problem
it a certain
is,
day my weekend.
yeah, no,
I
we're
don't know how
here.
that's gonna work.
And the problem is that the classes in Hattiesburg do not consider that Hattiesburg student to drive to the coast. Which would be nice because it's not that far, but the problem is that your schedule would never allow you to do that. Unless that's the only class in the day, which is only if you're taking very good credits.
Test, 1, 2, 3. Test. Good round,
Yeah, that's gonna be on Monday.
Oh.
During your lesson class today, all of my labs.
It's like, if you write it, write it out on paper. It's just like, it's everybody.
I'm gonna be like,
Right, those are, that you can write out.
I would say that you have to figure out the whole thought process, you're not gonna sleep.
I ain't got no like.
Oh, I wish I had a better understanding. I think that it's part of the.
Give me a
Especially in GI, I think it's
Oh, no,
it's tenfold. I remember, I think
Enough for me to need a job.
somebody down the course was like, they're GIS. And I'm like, oh my god, I'm on something, it's just so way above my head. And I'm like, no, GIS is way above my head. I don't know, apparently 3 semesters ago. Because remember, I always called me to work. That was like, it's a little, the concepts and the definitions, but I don't know them all by, yeah, me neither. I don't know them all by hand, I just know how to make sense of it. You know, what's your you guys should be like happy to take some. Architect does everything for them. When I took GIS, I was like, can't do that. I mean, I can't do that, but it's just like, wow. Because I took it with the free open source software. You basically have to tell every single thing for the software to do. And if you're doing like combination map algebra, it was easier for me I would do tables, and I would like, let's say I'm modeling erosion. So I would get like all my layers, soil, land cover, blah blah blah, and then If you're trying to set kind of like vulnerability to and then what I would do is, like in the whole calculation on the whole raster cells, I would classify the degrees. Like I would say like if you have this little a very high value on your slope, then you would vary. I mean, I would have like 5 notches, like high, super high, medium, low, very low. And I would look at how much slope it is and 2.8% slope, that would be low. And I would classify it like all of this white thing. So you would create those layers and then I would so you would classify another column, because they would have 5 classes. So I'm about to manually, like, not manually, but I will have to classify myself. Because it's not enough to do it. And we didn't know how to reclassify on the day. And it was fun. It's just like the names of the doesn't make so much sense, like our oh, okay. And then the house is right there. And you know, now they have this program for now it does not for students. They're not used to mark. No, yeah, they always have mark in parts because that's a commercial. Yeah, they don't have one already. But the other one was what's it called? Open source. It was ILW. Integrated land, water, resource something, E blah blah blah. No, it's like integrated land, water, and blah 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 system. Computer informational system. It's a pretty cool thing. It never crushed. Wow. This was good. Like it never crushed on me. Do you ever still use it sometimes, or do you like? I don't know why. I meant to use it. I meant to get to the new version. I wonder how they would do it. Because I'm trying to understand. I'm trying to learn because I came in contact with ArcMap last semester, and they learn very differently, but the way they consume things. And when I use the other one, when I come to ArcMap, I try to do things in the detour and very like long way, and then say, no, it's when we're all doing that. It's not. And the other one is like they never go to the office. Yeah, you always have to do like outline and consider all the default values was until I it was funny, I'm probably very gay. Yeah. I would be, I'd be numbering them. Yeah, that. I don't know, but I still, I haven't done the, I haven't been today, but I'm thinking today, because I wasn't here. Which is actually about the one with the ending,
I didn't take it. I took it in class.
You remember a little bit how you can see because that actually didn't record that day.
Yeah, you haven't do that.
Let's see.
All right, how's it going?
That's what I was thinking, set it up. Yeah. Testing. Hello.
Hey.
Dr. Graber, can you say something as if you're lecturing, testing, webcam as a backup.
Hey, I'm lecturing.